I think madam still not started.
Okay.
Madam is waiting for others to join. The first slide is just showing the list of topics into this week, which we are going to revise or see.
Okay, thank you.
Hello, am I audible? Hello.
Good evening,
Yes,
ma'am.
ma'am.
You are audible, madam.
Yeah, so very good evening to all.
Good
Okay,
evening,
so
ma'am.
we'll start. So in this lecture, we will cover whatever theory we have done in week 5. So I'll start with the 1-1 function, that means injective functions. Then we cover exponential function, then a special type of exponential function when we take our the value of a to be equal to e, which is known to be the exponent. And then we will cover the composition of two functions. So in the composition of two functions, the main problem is how could you find out the domain of composition of two functions. So this is the important topic in this composition of function. So mainly they will ask about you to cover the domain. That means what will be the domain of f composite g. If f and g are given to you, how can we find out the domain of composition of two functions? So this is the one thing I want to cover in details. So let's start with 1-1 function. So we know that what is a function. So what is a function? So you know that a function is a map from a set to another set which satisfy two conditions. And those two conditions are that every element of your domain should get mapped to some element and that element should be unique, right? So if f is a map from a to b, so if it is a map or a correspondence or a rule, you can say. So if you have a rule or a map from a set to another set, then we say that f is a function. F is a function if it satisfies two conditions. The first condition is if then we say f is a function if for every element of a, that means for every a in a, there is a unique b in b. There is a unique b in b in such a way that this function will take a small a as an input and map this a into b. That means B has a pre-image and that pre-image is nothing but A. But every input value should get mapped. So that means for every input, we need an output. So this is the first condition that a map should satisfy if it want to become a function. So first
I have a doubt, ma'am. Like in polynomial function should be a continuous one, right? That is, we can draw the graph without lifting the hand.
Correct.
Is it same for the function also, or there can be breaks in a function?
No. Polynomial is a one type of function. So there are several type of function: polynomial function, trigonometric function, right?
Okay.
Exponential, logarithmic. So polynomial is a kind of function.
Okay.
Yeah.
So in general, we can have breaks in a function,
Correct.
right? We
Right.
can have. We can have.
You
Okay.
can have discontinuous functions too. Those functions are discontinuous functions.
Okay.
So for a function, we define all such properties. That means for a function, we define limit. For a function, we define continuity. So that means function we already have. Over this structure, over the function, we are defining some other qualities of that particular function. So you can
Okay.
assume that limit, continuity, differentiability are qualities of that function.
Okay. Thank you, ma'am.
Madam,
Ma'am,
unique B, I am not
can
able
you
to
repeat
understand.
again for this? I am
Sorry, one by one.
joining late,
Yes, sir.
ma'am.
Wait. Yes, Nareen.
Can you repeat once again, ma'am? I am joining late, ma'am.
Yeah, I'll
Some
repeat again.
network issue.
Yeah,
Madam,
I'll repeat
unique
again.
B, I am not able to understand for a function because x square, f of x is equal to x square. It is a
It is a
function, no,
function,
madam?
but it has to. So that means for a input, you are getting a unique output. So for an output, you don't have two types. So I'll get back to the example x square. Okay. So first understand the definition. So if you have a map from a set to another set, and if that map satisfies these two conditions, that means for every value of a, you have some output, and that output should be unique. So for example, if I give you a map f from a set A to a set B, and suppose this set has four elements, 1, 2, 3, 4, and I'll map these four elements over some other elements of B. So suppose B contains some alphabet. So suppose A, B, C we have. So if I say that F maps 1 to A, F maps 2 to B, 2 to A2, 3 to A, and 4 to A. Now, is this map a function? Is this a function?
No, this is not a function as per above.
Why is not a function?
A function only, but it is not a one-to-one function.
One. Yeah, it's not a one-to-one
One-to-one
function,
function.
but it is a function because see, for a function, we need to check two properties. First is every A, that means every element of A should get mapped. So here we have four elements in our domain set A, right? So there are four elements. So four elements are 1, 2, 3, 4. So F is taking 1 and mapping 1 over A, right? F is taking 2, mapping 2 over A, right? Similar for 3 and similar for 4. So that means every element of A get some output, right? So if you consider 1 as your input of this particular map F, then 1 has an output which is A, right? And here another word is unique. So unique means one input should get mapped to one output only. So that means if I give you input, you are able to give me a unique output. So for example, if I made this function in some another way, so suppose I'll say that, okay, 4 is going to B, and 4 is also get mapped to C also. So that means if you give me 4 as an input and say that this is our map F, then I cannot say that which output, about which output you are talking. So it is possible to for 4 to get map at B, also to get map at C. So that means here this 4 has two outputs, which we don't want in a function. So if it is a function, it should give us a unique output for a single input. It should not give us a multiple outputs. Okay, so this is not a function now. If I say that 4 is mapping to B and 4 is mapping to C also. So in this case, it is not a function. But previously, when I say some like this, so now it is a function. So we have to verify two words. First is every, that means every element of your domain should get mapped to somewhere. And another one is unique. So that means for an input, you should have a unique output. Is that okay?
Yes, ma'am.
Unique word is cleared. Unique to the domain, I mean X, whatever, A, set A. You can have only one point in B. You cannot have 2 points in B. One should not go to A and B, or one should not go to A and C, something like that. That is uniqueness, correct, no, madam?
Yeah, uniqueness means single input go to single output only. That means
Single,
one is mapping to A, and then one cannot map to any other element.
any other. Good. Thank you, ma'am.
And now let's go to the example y is equals to x squared. So here also, if you take any x, so suppose this is your function. Now there are several ways to represent a function. One way is this type of way. So for example, if you have finitely many elements in your input set, you can explicitly give us the output set and say that, okay, this is a mapping. So this is a one way of expressing function. But it's not that common. It's just used for understanding the concept of function. Okay. Another way is a function can be expressed by some equation. Now, what is the equation? So we will give you some relation using variables. So here x and y are variables. So that means you can place some value in place of x and you can get some value in place of y. So such kind of relations are known to be equations or expressions. So we can express a function using equations or expression too. So for example, here y is equals to x square is one kind of expression which we can use to demonstrate a function. So we'll say that f is a function from real number to real number, which is given as f of x is equals to x squared. So that means for any real number, I'm getting output which can be expressed in terms of x squared. Okay, so this is a very common way for expressing a function. So we will give some expression instead of f of x. You can also write y, because y is an alphabet which we often use for dependent variable. So dependent means here y is actually dependent on x. That means if you choose x, you can get a y. That's why it's known to be a dependent variable. So in place of f of x, sometimes we write as y2. So this is a very common way to expressing a function. That means y is equals to f of y is equals to x squared. So here observe that if you take x is equals to 1 and if you take x is equals to minus 1, so suppose I'll take x1 to be equal to 1, x2 to be equal to minus 1. Then here f of x1 which is equal to 1 and which is 1 square means 1, correct? And if you compute f of x2, that is also minus 1 the whole square, which is 1. So here we are getting that f of x1 is equals to f of x2 is equals to 1. So that means for two input, I'm getting same output. So it is possible in a function that for two inputs, we can get the same output. So yes, we can say that yes, this y is equals to x square is a function. Y is equals to x square, or you can write f of x is equals to x square is a function. But it is not a 1-1 function. So what are the 1-1 functions? So 1-1 function are those functions, again, they are functions and we are defining some extra properties over those functions. So if that particular function has some extra properties, and what is that property? That for an input, for two distinct input, we should get two distinct output. So for example, here we have two distinct inputs, right? We have two distinct inputs means we have two distinct value of x. So one value is 1, another value is minus 1. So these are two distinct values. But when we compute the functional value or when we compute the output related to these two inputs, what we are getting? We are getting 1 for both inputs, for both x1 and x2. So that means here x1 is not equals to x2, but the value of function which is f of x1 is equal to f of x2. So we don't want these. So this function does not satisfy this particular condition. That means if you have two distinct input, you may get the same output, right? So this condition, whatever, suppose a function possesses such type of condition, those functions are known to be 1-1 function. Okay, so let's formally state what is the 1-1 function. So there are several names for 1-1 function. Someone says 1-1 functions or 1-to-1 functions. Right? 1-1 functions, 1-to-1 functions, and another word is injective functions. So what are those functions? So an injective function is a function for which if we have two distinct inputs, we will get two distinct outputs, right? So how can we mathematically write this thing? So we'll say, again, we have to assume a function. So suppose let f is a function from a to b. Right? So this is a notational way to write that f is a function from a to b. Here a is a set of domain, b is a set of codomain. Okay, so suppose f is a function from a to b, then f is said to be 1-1. F is said to be 1-1 or injective if for two distinct inputs. So that means if x1 not equals to x2, and these two are from input set A. So if for two distinct inputs x1 not equals to x2, we can imply and we can surely say that the output values, that means f of x1 and f of x2, these two values are also not equal. Okay, so if this condition happen, then we say that function is nothing but a 1-1 function. Okay, is the definition is clear? Any doubt? The definition of 1-1 function?
Please give the example.
Yeah, I'll give the example. So this is the basic definition. So for example, I'll take very simple example. So suppose we have an equation of line. So then suppose I have f of x is equals to 3x minus 5. Okay. So this is an equation of line. And we want to say that is this a 1-1 function or not. So it is a 1-1 function. But how can we prove it that it is a 1-1 function? So for that, what we'll do, we'll use the definition. So in definition, we have two parts. So this is our definition, right? So in this definition, we actually have two parts. So first is the assumption. So assumption says if you assume x1 not equals to x2, you should be able to imply f of x1 not equals to f of x2. And if this statement is true, we can say the function is 1-1 function. So suppose I'll assume the x1 not equals to x2 case. Okay, so suppose x1 not equals to x2. Okay, so if x1 is not equals to x2, and again x1 and x2 are two real numbers because we have equation of line, so function is from real number to real number. Okay, so x1 is not equals to x2, and we can simply say, okay, 3 times of x1 is also not equals to 3 times of x2. This is our assumption. Okay, that x1 not equals to x2, I'm assuming two distinct input points. And I want to prove that related to these two distinct input points, I'll get two distinct outputs. That is my claim. And I want to prove that claim using some steps. Okay, so what are the steps I'm using here? So this is assumption that x1 not equals to x2. So that will obviously imply 3 times of x1 not equals to 3 times of x2. And similarly, 3 times of x1 minus 5 is also not equals to 3 times of x2 minus 5. So we can say that, okay, f of x1, because this is f of x1. The expression is 3x minus 5.
What
So
is
this is not equals to-
3x2 here?
x2 is another input point. So we are assuming two distinct input points.
Okay.
Any two real numbers you can take. But for abstract, because obviously this condition should be true for all x1 and x2 belonging to A, right? So for abstractness, we are taking any two general. So in place of x1, x2, you can put any values. It doesn't contradict our steps, right? So if we prove any in general for any x1, x2, it will be true for any particular values of x1 and x2, right? So that's what we do in proof. So in proofs, we prove the abstract part. Abstract part means here in place of x1, x2, you can take any values. So suppose you can take 2 not equals to 3. Right? So if 2 not equals to 3, you can easily imply that, okay, using these steps, I can say that f of 2 is also not equals to f of 3. Okay, so that's why. So here I assume x1 not equals to x2, which implies f of x1 is also not equals to x2, f of x2. So here what I proved that if you take two distinct inputs, that means if x1 not equals to x2, x1 and x2 are 2 points from your domain, then we can imply, and we can obviously say by these steps that f of x1 is also not equals to f of x2. So by the definition of 1-1 function, we can say that f is a 1-1 function.
Or in other words, we can say that for a input, it should have a unique value.
No, that is contained in definition of function. So function says that for an input you should have a unique value, but it is possible that two inputs will get mapped to a same value. Right? So for example, I'll just state a simple example. So suppose the same sets I have 1, 2, 3, and here I have A, B, C, D. Okay. So suppose I'll say 1 get mapped to A, and 2 also go to A, and 3 goes to C. Now, first question is this a function?
No,
Why is not a function?
because 1 and 2 are getting a same value. It's not unique.
It is a function
It is
only,
a
but it is
function.
not a one-to-one.
1-1 function. It is a function because for function, we need to check every and unique, right? So here every is satisfied because for every element of A, we have some output. And unique also satisfied. That means one is getting mapped to only single output. One is not getting mapped to any other output. So that's why every is there, unique is there. That's why it's a function. But it's not a 1-1 function. Because for two distinct input, we are having same output. Okay, so it is a function, yes. So not a 1-1 function. Why it is not a 1 function? Because f of 1 is same as f of 2, which is nothing but A. And obviously 1 is not equals to 2. So that means for two distinct inputs, we are getting the same output. That's the difference between 1 1 and function being a function and being a 1 1 function. So if it is a function, it should satisfy these two conditions. That means first is every element should possess some output, and the second condition is that every input should possess some unique output. So that means if someone gives you a function, and if they say that this is the input, you can surely say that okay, if this is the input, this will be an output. Okay, so for example, if this is a function,
What is onto function?
yeah, so for onto function, what happen? Your codomain set will become the range set. So I'll define what is the range of a function. Uh, so a range is nothing, but we have to collect all those elements from your codomain, which can be an output. So for example, here in this function, this A has a pre-image. Pre-image means there is an element in your domain set which is getting mapped to this particular element A. So here we have two elements, 1 and 2, which has an output equal to A. So that means this A has some pre-images. So this will contain this A will be in our range set, and the C will be in our range set. So a range of a function is nothing but a subset of your codomain. So you have to filter out those elements from codomain which has a pre-image. That is known to be your range set. And if the range set is same as the codomain set, then we say that that function is an onto function. Okay, so I'll get back. I'll also state the onto function. So is there any doubt in 1 1 function or injective function?
Is a function,
And
madam.
Hmm.
But
Yes, it is a function, but it is not a 1 1 function.
no, but for 0, it is not defined, no?
0.
Undefined. 1 by x, 1 by 0 is undefined, no?
But that function has domain as r minus 0. Okay, so that is another thing. So for example, if someone
Okay.
gives you f
We
of
have
x
to
is equals
define
to 1,
domain also. Like set
then
A
f
should
is
be defined.
right. So it is I mean trivially assume that the domain is real number minus 0.
If somebody says domain is real number, then 1 by x is not a function.
Yeah, correct. It is not a function because it is not defined for x is equals to 0.
Okay.
Excuse me, ma'am.
Yes, Rajman.
Ma'am, please take one example more.
Yeah, I'll take the example on 1 1 function. So I have 2 to 3 ways by which we can judge that it is a function, that given function is 1 1 function or not. So I'll first state these ways, and then we will go to onto function. But yeah, we won't study onto function in detail. I'll just give the definition because it's actually pretty hard to check that a function is onto or not. So that means finding
Ma'am,
a
please take
range.
one more example of algebraic method how to check
Yeah,
injective function.
I'll take. I have one example. So what I was saying that it is actually not easy to find out the range of a function. It is easy in some cases. Some cases means if a graph of function is given to you, then you can find out, or some special type of expression is there, then you can find out. But in general, it is actually a tough task to find out the range of a function. Okay, so first let's discuss some of the ways, and then I'll take one example. Okay, so some ways or some test is there which we can use to check that a given function is 1 1 function or not. Okay, so first one is just by definition. So we have to check the statement. So check the statement. So the statement which we used in definition, that if x1 not equals to x2, then it should imply f of x1 not equals to f of x2. So this is a one statement. You can either you can check the statement. So it means you can find out two distinct x1 and x2 for which the output is not same, and you can say that okay, because of this the statement is not true for these particular values of x1 x2, given function is not one. So for example, if I take f of x is equals to x square, then obviously we can take x1 to be equal to 1, we can take x2 to be equal to minus 1, and we can say since x1 not equals to x2, but f of x1 is equal to f of x2, which is equal to 1. So we can say that since this statement is not true, or we can say false for x1 is equals to 1 and x2 is equals to minus 1, the given function is not 1 1. So this is a one way. Given function is
I'm taking a numerical values, no, madam.
yeah, any numerical value. If you can guess using the expression, because we can guess that these values will work for this particular function, x square function. Correct?
Generalized version, we will not be able to prove.
For generalized version, one thing is just by expression we can guess. So whenever there are quadratic functions, the quadratic means whenever the function involves a x square type of term, it generally need not to be a one function, because we know for some negative and positive values we can get the what you can say, the same output, right? So this is a one way, but you can check the function using the horizontal line test. That is the best test we can use for checking the
Ma'am, in this type of question, the best approach to find the one injectivity, take a one example for a square and do the square, and we get all the
Yeah,
injective.
I'll take one example. This
Done. It's okay. But horizontal line test without graph, we will not be able to do, no, madam. Or
Yeah, but we know that in general, if you have some quadratic function or polynomials, then we know how to draw a graph of a polynomial, right? So
yeah.
those things we can do. The shiftings we can do, but in general, yes, obviously, in general, it's a tough thing to find out the one also. But by the expression, either you will get such values of x1 and x2, which you can say that, okay, if I put these two values, I'll get same output. It depends on your practice, right? So you cannot immediately find out x1, x2. You have to do some work or observe the expression. Okay. Otherwise, if you feel that, okay, this function could be a one function, then try to prove that it is a one function either by checking this particular expression. Okay. So suppose I'll take for proof, I'll take f of x is equals to 3x plus 4 upon 7x plus 9. So suppose this is a function. I also don't know it is a one function or not, but let's try to find out it is a one function or not. Okay. What I can do, so I can think about, since it's a linear function, it is possible to become a one function. Okay, it is possible that this function could be a one function. So suppose I'll try to break it down. So suppose I'll take 3x upon 7x plus 9 and then plus 4 upon 7x plus 9. Okay. Then I try to further break it down. So suppose I'll say that f of x is 3 upon 7 plus 9 by x and plus 4 upon 7x plus 9. So I have what I want to do. I want to separate an x in such a way that I can work with only x. So for example, so now if we take x1 not equals to x2, then obviously if x1 not equals to x2, then this 9 by x1 is also not equals to 9 by x2, and the 7x1 plus 9 is also not equals to 7x2 plus 9, because it's an obvious thing. If you take two real number and if you multiply and if you compute this number, that 9 by x1 or 9 by x2, those two numbers will be distinct, right? And similar thing here also, that 7 of x1 plus 9 is also not equals to 7 of x2 plus 9. So we can say that, okay, since these two terms are distinct, I can say that 3 upon 7 plus 9 of x1 is also not equals to 3 upon 7 plus 9 of x2, right? And since this term is these two values are different, I can simply say that, okay, 4 upon 7x1 plus 9 is also not equals to 4 upon 7x2 plus 9. And why we can say? Because ultimately we are multiplying and dividing by some constants. So here 3 is a constant, right? So we are just multiplying 3 to the both sides, right? We are adding 7 both sides and we are taking reciprocal both sides, right? So we are doing the same type of operations. So ultimately, since these two terms are not equal, their addition is also not equal. So we can say that, okay, 3 upon 7 plus 9 by x1. This is also plus 4 upon 7 times of x1. This is also not equals to the addition of these two things. 9 by x2 plus 4 upon 7x2 plus 9. Right. So ultimately, we can say that, okay, f of x1 is not equals to f of x2. So this is a way, another way we can check that a function is one or not. Okay, just by using abstract x1 and x2. But again, it's it needs some practice to get such an handiwork. But you can always find out two values if you think that it is of one. It cannot be a one function.
Madam, again coming back to that domain, in the last given example, if one of the
Yeah.
x is one of the x is minus 9 by 7, then
It
the
won't be a
denominator
function.
becomes 0, no?
Correct. So we are assuming that it is a function from real number minus 9 by 7, this point.
So in general, this minus real number minus something is not at all given. So we
Yeah.
assume that it is a good function.
Yeah, we can assume. They will mention the word function. So if you say that consider the following function and then expression is given to you, you can assume that okay, it is a function, and then you have to check one.
Okay, so it is assumption, or maybe explicitly it has to
Mention.
be mentioned.
Right.
No, if there is a general question which doesn't mention the domain, then accordingly the definition of function, this is not a function. Correct, no, madam? Again, I am
Yeah,
just
correct.
stuck
Correct.
in that particular place itself.
Correct. So if explicitly domain is not given to you, then obviously we can say that it is not a function.
Okay.
Over
Ma'am,
real
this
numbers.
question is going to very long, ma'am. Very.
Yeah, but it depends question to question. See, in some question you can find out the values of x1 and x2, and you can immediately.
Ma'am, when doing cross multiplication and find the injectivity, that's a good for. It's going to very short time.
Yeah, it's okay. You can do in any ways. So let's go to the next point. Okay. So this is a one point that you can use for checking oneness or injectiveness. Another point is we can reverse the statement. Reverse the statement means now we are initially we was checking that if we get two distinct inputs, we want two distinct outputs. But if you take same outputs, then it should imply same.
Excuse me, ma'am.
For example.
Excuse me, ma'am.
Yeah.
Ma'am, please take example of x cube. How to prove in injectivity?
X cube is kind of obvious, right? So if you take cube of two distinct real numbers, those will be different. So if x1 not equals to x2, then it's kind of obvious that okay, if these two numbers are not equal, their cube is also not equal. You can check this by taking any real number. So for example, 2 is not equals to 3. So if you take the cube, obviously the cube will be not equal, right?
So,
So
ma'am, if the powers are even, there is a possibility of getting
yeah.
not getting 1 to 1. If the power is odd, there will be a chance of getting
chance
1 to 1
of
function.
getting a 1 to 1. Yeah, 1 function. So for x cube, we can check. But see, if the polynomial is there, we can know how to draw a graph of a polynomial. So you can use the that concept and plus the horizontal line test. So, okay. So the second point is I want to reverse the statement. So you can also check the statement. So check the statement. So here the statement is
Explain negative and positive value does not work. I mean minus 3 and 3.
minus 3 and 3 will still have different cubes. Minus 27 and 27, right? So if f of x1 is not, so we want to reverse the statement. So here what you do, you'll assume that, okay, you have a same output. So for a single output, we need a single input. So that means this should imply x1 is also equal to x2. So this is used when we want to check that given function is 1, 1. So that means it is mostly used for proving oneness. 1 functions. So for example, if you if you think that given expression might be a 1 function, you can check this statement. So if f of x1 is equals to f of x2, you can imply that x1 is equals to x2. So this is another statement which we can use for proving that a function is 1, 1 or not. So for example, simply we can take, again I'll take the equation of line only. So suppose I have 3x plus 1. So if you assume f of x1 is equals to f of x2, so that means we are assuming 3x1 plus 1 is equals to 3x2 plus 1. So this will implies 3x1 is equals to 3x2. Yeah, we can cancel out 1 from both sides. So it means x1 is equals to x2. So that's how you can check this particular statement. So it's just nothing but a negation of the above statement. Okay, so negation, and also we kind of converted the hypothesis and the result. So here we are assuming f of x1 is equals to f of x2 and trying to prove x1 is equals to x2. So this is second statement you can use for checking 1, 1 functions. Okay, and the third is the horizontal line test. So in the horizontal line test, what you have to do, you have to draw several horizontal lines. So we know that horizontal line is nothing but a line which is parallel to x-axis. So such a line you have to draw. And here you have to check that is there any line which can intersect the given graph of a function more than once. So for example, if I draw this function, so suppose this is my function, then here there are several horizontal lines which can intersect the given graph of a function more than once. So suppose I'll take this particular line, then this line is intersecting at 2 points to my given graph of a function. So at these 2 points, what is happening? So suppose here the value of x is, you can take any value. So suppose I'll take 1, and here the value of x is 5, minus 1 and 5. And suppose this is the value of y to be equal to minus 1. Then can you find out the coordinate of point A and B? What will be the coordinates of point A? Coordinates of point A.
0 and -1.
A point is over the line y is equals to -1. So the x coordinate is -1, right? And the y coordinate is
-1,
also
0.
-1.
Acha, -1, okay.
And the coordinate of point B will be, the x coordinate will be 5 and the y coordinate will be -1. So here what is happening, since this line is intersecting twice to our graph, we are getting that for two distinct inputs. So that means for two values, that means f of -1 is same as f of 5, which is equal to -1. So that's why using the horizontal test, we can say that it is not a 1-1 function. Okay, so it will imply f is not a 1-1 function. Okay, so horizontal test means you have to draw several horizontal lines, and if you can find out a one horizontal line which is intersecting the graph of a function more than once, then you can say that that function is not a 1-1 function, or whatever function represent that particular graph is not a 1-1 function. Okay, so mostly whenever we have a quadratic polynomial, so suppose I have a polynomial p of x of even degree. That means even degree polynomial. So we know that whenever we have an even degree polynomial, then this polynomial either goes to plus infinity from both sides. So that means as x goes to infinity, this polynomial goes to infinity, or the reverse of this can happen. So that means it goes to minus infinity. Right? Whenever x goes to minus infinity, x goes to infinity. So these two scenarios can happen for an even degree polynomial. We know this thing by week 4, right? So in that case, what happens? So it is always possible to find out a horizontal line which can intersect the graph of polynomial more than once. Okay, we can always find such a line. So that's why whenever we say, whenever we have an even degree polynomial, we can say that, okay, that function, this polynomial is not a 1-1 function. Okay, and again, polynomials are function. So you can say that, okay, this function is not a 1-1 function. Is that clear? Any doubt in horizontal line test? Any comments?
Yes, ma'am, but we cannot say the same for polynomials.
Sorry, your voice is breaking.
No, we cannot say the same thing for odd degree
Correct.
polynomials.
Yeah, because for odd degree polynomials, we have an example, f of x is equals to x cube. So it is an odd degree polynomial, but it is also a 1-1 function.
Yeah, okay, madam. What I meant was you cannot always say that if it is odd, it will be 1-1.
Yeah, that's also fine. That's also correct. Because suppose I'll take, yeah, you can easily find
There
out
is an
the
example in the what do you call assignment, not this assignments. It was there. Like I felt it is cube. It is there, but you have y coordinate is -5 or something like that, and it there is a uh, change of direction
Okay.
above x. Above x,
Mm.
there is a change of direction. So then it is
Not a
horizontal
1-1.
line test. It is failing.
Right.
Even the higher powers of order, say for example, x power 5, even in that case also the horizontal line test will fail as it touches the x-axis flatter.
Yeah, it will be more flatter, but it will work because it is becoming flatter, but it never touches 0. So for example, x to the power 5 we have now. So in
Mm.
x to the power 5 also, if you take any two distinct real number x1, x2,
Mm.
the fifth power will be different.
Yes.
Hmm.
Then how will be the graph for x power 5?
It's
Can you draw?
actually look like it is touching more than one points at x-axis, but actually
Okay.
not. When you go to Desmos and try to zoom it, you'll
Okay.
find that okay, there is a little gap between the x-axis and the graph.
So we'll get distinct output for these functions.
Correct.
Okay.
X to the power 5 too.
Yeah.
Okay. So these are the ways we can by which we can judge the function is 1 or not. So mainly, but these are actually very what you can say, they are not precise way. So it is possible to use this way, and sometimes it's very difficult to find out a function is 1 or not. But in our course, whatever example is given to you, either you can find out two distinct values of x1, x2, which will say that okay, this function is not 1, or you can use these three tests to show that your given function is 1. Okay, these are the only methods you have to use for proving 1 functions. Okay. Any doubt? Any doubt other than this? So now let's define what is an onto function. Onto, or it's also known to be surjective function.
To check on vertical lines.
Yeah, so vertical line test is used for showing that given graph defines a function or not. Okay, so vertical line means vertical line test. This is for saying that given graph is represents a function or not. Graph represents a function or not. So for example, if you consider the graph of a circle, so suppose assume that this is a circle. Okay, so this is a graph is given to you, and if someone asks that is this particular curve or graph represents a function or not, so here you can use vertical line test. So again, vertical line test is similar to horizontal line test. We have to draw several vertical lines, and if there is a vertical line which can intersect the graph more than once, then we can say that this particular graph does not represent a function. So it's a well-known fact that the graph of a circle does not represent a function, because assume that it is a circle at origin with radius 2. And if you draw a line x is equals to 1, it will intersect the graph more than once. So it means for a same input, we are getting two outputs, right? For a function, we need uniqueness. So here, because of this vertical line, for a one single input, we are getting two distinct outputs, right? So whatever the output here will be, you can compute using the equation of circle. So that's why vertical line test is used for saying that a graph represents a circle or not. Yes, Naren.
No, madam. So this x square plus y square is equal to 1 cannot be called as a function. It has to be called as an expression. Isn't it?
Correct. That's why x square plus y square is equals to 1. If you consider it's not a function. That's why for function we use two different expression. This one, sorry, 1 minus x square. And another is y is equals to minus of under the root of 1 minus x square. That means one expression for this upper semi-half circle, and another one is for the lower semi-half circle. It's a very well-known question. I mean, if someone asks you the definition of circle, and if they assume that you understand the definition, they immediately ask that is the graph of circle represents a function or not. So you have to say that okay, it does not, and why it is not? Because it fails a vertical line test. Okay. Clear? Any doubt? Fine. Let's go to onto function.
For same thing, if domain is given only, okay, domain is only for x line. Even domain is defined, then also this x square plus y square equal to 1 is not a function at all, isn't it, ma'am?
Correct. Because you cannot choose a segment of you can
Yes.
choose a segment. So for example, if I say that okay, my domain, no, still no won't.
Because x will be
Mhm.
negative as well as positive. In both cases, your vertical line test will fail.
Will fail, correct.
Okay, ma'am.
So now what is an onto function? So we know that what is the range of a function? So range of a function f. So it is nothing but a subset of codomain. So it's a subset of the set B. If we are assuming f is a function from A to B, then a range of f is nothing but a subset of b in such a way that if I write the set comprehension notation here, then I have to collect all the elements b such a way that b is an element of b, and there is an a, there is an a in a such a way that this f will take a as input and give us b as an output. So we have to collect all those elements from output which have some kind of input or some kind of pre-images. So here we say that a is the pre-image, or a is a pre-image, because pre-images can be more than once for a function, right? So here a is a pre-image of b. Okay, so this is a terminology we usually say when we say that a function is from a to b, and if f of a is equals to b, then b is known to be the image of a, and a is known to be a pre-image of b. Okay, so image means which we are projecting type of thing, and pre-image is what we are projecting type of thing. Okay, so if a is your input, we say that a is a pre-image of b. So we have to collect all those elements from codomain which has some kind of pre-images.
So image is output and pre-image is input.
Correct. Image is output and pre-image is input. So this is your range set. And if for a function, so if the range is same as codomain, so if range of f is same as codomain, then we say that f is a onto function. So image is same as codomains means for every output we have, for every element of B, we has some kind of pre-images. That means every element of B has some pre-images. So that means there is an input which we can associate with any element of your codomain set. So known to be an onto function. So for example, we can take f of x is equals to x cube. Right. So suppose this is a function, but yes, if you want to check the what do you say, that onto functions, we need to define what is a codomain of this function. So suppose I'll say that it is a function from real number to real number, then whatever set is here, this is known to be your codomain. So if f is a function from real number to real number given by this expression f of x is equals to x cube, then it is an onto function. Why? Because for every element, for every element, for every real number, you can find out the cube root of that particular real number, right? So we can find x to the power 1 by 3, which is actually a real number. And if you take x to the power 1 by 3 to the power 3, we'll get x. That means for every real number, we have a cube root. So that's why we can say that it is a onto function. But again, checking onto is also not easy.
Ma'am,
Yeah.
ma'am,
Yes,
what
sir.
did you just told right now? I didn't got it. That we can find x to the power 1 by 3. What is that?
Yeah. So if you have any real number and you want to find another real number which will map to your given output. So for example, if I want to find out so for every r in r, so suppose I'll take a particular number. So for 5 belongs to real number, I can find out another real number, say y belongs to real number, such a way that if I compute y cube, I'll get 5 as an output, right? So that means if I compute f of y, I'll get 5 as an output, right? So in place of y, what do you put? We can simply put 5 to the power 1 by 3, and we know that it is a real number. So if you compute 5 to the power 1 by 3, this is same as 5 to the power 1 by 3 the whole cube, and which is same as 5. So that means for 5, I have some pre-image. And this is true for every real number. For every real number, we can find out the cube root. For in cube root, we don't have any problem. In square root, we have to consider the positive numbers only. But when you have cube, you can consider anything, right?
And this is for onto function, no?
This is for onto function.
But ma'am, we can also see it from here that for even if we take negative integer, it will give us unique
Cube
codomain.
root, correct.
Yeah. So how could this be an onto function, ma'am? Since each and every image will each and every pre-image will have a unique image.
Means
मैम मतलब ये जो क्यूब रूट जो होगा मैम, मतलब ये जो
हम्म
क्यूब है,
हम्म
कुछ भी एक्स टू दी पावर क्यूब, इसमें अगर
हम्म
नेगेटिव इंटीजर लेंगे
नहीं
तो
नहीं नहीं
नेगेटिव रिजल्ट देगा, अगर पॉजिटिव इंटीजर देंगे तो पॉजिटिव रिजल्ट देगा।
Yeah, so it depends on your output. So यहाँ if I take
तो
the
मैम
positive
ये तो
output,
1 1 हुआ ना?
हाँ तो ये 1 1 भी होता है ना. So f of x is equals to x cube is 1 1 plus onto. So 1 1 is a different property and onto is a different property of function. So it is possible to get both properties. That is known to be our bijective functions,
ओके मैम, ओके।
right? So f of x cube is actually a bijective function.
F of x square is neither onto nor
Or
1 1.
1, correct. But we can make functions onto. So what happened in some cases, as you learn in week 6 when we define logarithm. So what do? We restrict the codomain. So instead of saying that, okay, so I can make f of x square to be an onto function. So suppose I'll take f is a function from real number to positive real numbers only, and define this function f of x is equals to x square. Then now it is an onto function. Now it is an onto function because I restricted my domain. So instead of considering real number as the codomain, I restricted the codomain to be r plus, and we know that the range state of this function is nothing but r plus only. So that's how we can make functions to be onto. Similarly, you can make functions 1 1 also,
Ma'am,
but it's very
hello.
easy to make them onto.
Excuse me, ma'am.
Yes, Rajman.
Ma'am, any algebraic method to find onto function, ma'am? Like
Actually, for onto, it's very difficult. If you follow the definition, it's actually kind of, for some function, it's kind of obvious. For example, x cube, it is obvious that it will be onto function. For equation of line, it is obvious that it will be an onto function. But in general, there is no particular expression we have to, or no particular statement we can check that for showing that given function is onto. That's why I say for finding out the function is onto, it's kind of little tough. So again, you can use the graph. So by the graph also, we can say that a function is onto or not. So I'll come to that.
Suppose I was coming to tell that. So any polynomials, regular polynomials, we can have a graph and then see whether it is onto or not. Okay,
Correct,
madam.
correct. So by the graph, how we can check? So if the codomain is not mentioned to you, you can assume that the codomain is nothing but the whole real line. Okay. So if codomain is not mentioned in the question, you can assume that it is the whole real line. So by the graph, you have to check this thing that if you draw any vertical line. So here is for example, I have a function. I'll draw any vertical line. Then this line should intersect your graph exactly at once, or you can say at least once. Okay. So by the graph, we can check that it is a function, that given graph is represents a onto function or not. That every horizontal line, or any horizontal line would be better. Any horizontal line should intersect the graph at least once. Because then only, so suppose I have a horizontal line here. So suppose this is my horizontal line y is equals to 3. And if this horizontal line is intersecting the graph of function at least once, so here it is intersecting twice. But if it is intersecting at least one, then you can say that, okay, surely I have some x naught here for which the function value f of x naught is nothing but 3. That means for this y is equals to 3, I have a pre-image. And if this is true for any vertical line, so for example, instead of y is equals to 3, I draw a vertical line here. This is also intersecting the graph at least once. And if I say that, okay, this graph is going towards minus infinity, then you can draw any vertical line here and say that, okay, this vertical line is intersecting the graph here. But what happens if I draw a vertical line above this particular curvature part? So for example, here, suppose this is one vertical line. So this is a vertical line which is not intersecting the graph at all, right? So that means for this value of y, we don't have a pre-image.
But when minus x tends to minus infinity,
This is possible that it goes to up. So for example, for assume, I say that, okay, this is as x going to minus infinity, the function is also going to minus infinity.
Okay. Correct. Thank you.
Right?
At least means, ma'am, it's going to cut the
At
graph
least once.
once or more time, no?
हाँ,
One or more
एक बार
time.
नहीं तो एक से ज्यादा बार तो इंटरसेक्ट करना चाहिए, at least once.
Okay.
Okay, so then we can say that a given graph is onto function on. But let's come back to the x square graph. So this is the graph of x square. Okay, something like this. So here, if you consider the codomain as the whole real number, then obviously it's not a onto function. But if you consider the codomain to be only r positive, then for r positive, if you draw any vertical line, any horizontal line here, then that line will intersect the graph more
Function
than.
is onto function, ma'am.
Yeah, so x square is onto function if you restrict your domain to r plus, then it will become an onto function. That means it is possible to convert a function which is not onto into onto just by restricting the domain. And this we usually do when we need bijective functions. Okay. So what is a bijective function? Let's state that also.
Bijective means both 1 1 and on 2.
Correct. Both 1 1 and onto. It's known to be a bijective function. Bijective or invertible is another word to use. We can use.
What ma'am? Invertible.
Invertible function. That means those function which possess an inverse function. So we'll define what is an inverse function when we go for the composition of two functions. Okay. So now we have the next topic.
Ma'am,
Which
1 1 function is not reversible, no?
1 1 function, the only 1 1 is actually not enough to say that it is inversible, because see, if you don't have if you don't have onto, then it is possible to get some element in your codomain which does not have a pre-image. So in that case, how we will map those elements if you want to construct the inverse, right? So inverse means if you go forward, there is a way to come backward too. So if there is no way by which I can go to, I can reach that place, then it's not possible. So that means only 1 1 or only onto does not imply that function is invertible or bijective. We need
For
both.
ma'am, for a single input, we can get more than one output. It is a onto function.
No, it's not even the function.
It's a relation then.
You can say that it's a relation, but it's
But
not.
ma'am, you are saying many one function is a onto function, ma'am. Also onto function.
Many one is actually not a function. Many one, I don't know what is many one functions, because yeah, there are some ways to define many one many one. I don't that what they define. But if they are saying function, then these are not functions, because for function we need uniqueness. Okay. So I'll go to composition of function, and then I'll go to exponential function, because exponential function topic is not that I mean, we can discuss it with very less time. But composition of function and domain of composition function, this topic I want to cover. Okay. So composition of functions. So what we want to do, we want to apply another function on image of functions. For example, I have a function f from a to b. I have another function g from b to c. Then I can construct a new function h, which takes inputs from the set A and give us output into the set C. And this function is defined as that first we'll apply g on the input value x, and over this value g of x, we will apply another function f. So this is also known to be f composite g of x. So this is called as composition of two functions. So that means we are applying function one by one. I'll apply first function g, then I'll apply the function f on that output. So that means the first input is x, then we will get g of x, and then we will get f of g of x. So f is applied on g of x. So such kind of functions are known to be composition of two functions. Okay, so now here one particular question is how we can find out the domain. What will be the domain of f composite g of x? Okay, so here you have to follow two steps, and why these two steps are required, I'll just mention. But before that, what do we understand by domain of a function? Okay, so domains means what? Okay, so domain means if a function's expression is given to you, you have to filter out all those real number for which that particular expression is well defined. Okay, so suppose f of x is given to you with some expression. Here you can say that some expression we have. Then what will be the domain? So domain is all those points, all those real numbers for which the given expression is well defined. Well defined means it should make sense. So it should not give us a complex number and not plus or minus infinity type of thing. Okay, so if these two scenarios is not happening, we can say that for that particular real number, the expression makes sense to us or it is well defined. So what we have to do for finding out the domain, we have to extract all those real numbers for which the given expression is meaningful. So it should not become plus infinity or minus infinity, and it should not become any complex number. Complex number means square root of minus 1 type of thing. Okay, so if such thing is not happening for that x, we can say that function makes sense and we can take that x in our domain set. So if f of x is given to you with some expression, it is a valid question to ask for domain. What will be the domain of that particular function? So now here we understood that, okay, this is the meaning of domain for finding a domain of a function, that extracting all those x for which the expression of function makes sense. Okay, but what happen if we have composite function? So f composite g of x we have. So how can we find out the domain of this composite function? So first thing is find domain of g and domain of f. Okay, so first what you will do, find out the domain of both functions f and g. And second thing what you have to do, you have to remove all those x belongs to domain of g. And why I'm saying domain of g, because this is f of g of x. So ultimately whatever x you want to take, first of all g of x should be well defined. G of x should be well defined means x should be part of domain of g. So if you want to find out the domain of f composite g, first thing we have to do, find out the domain of g, find out the domain of f. Second thing is you have to remove all those points from domain of g. And why we are removing domain of g? Because first we are applying g, that's why. So we have to remove all those x from domain of g for which g of x, so that means if you compute g of x, it is not a part of f of domain of f. That means we have to remove all those elements from domain of g for which g of x is not a part of domain of f. Because if g of x is not a part of domain of f, we cannot talk about f of g of x. So we have to apply f on g of x. And if g of x is not a part of domain of f, that means that particular expression is not defined for g of x. So composition of function means we have to apply functions one by one. First we will apply the function g, and whatever output we will get, on that output we will apply f. So whenever we find out the domain of composite function, we have to take care of this second point. So that's why whenever you find out the domain of composite function, don't go by the expression. So by the expression means do not find out the expression for composite function and then find out the domain. First use these two steps. So let's take an example what I want to say. So for example, if I take f of x is equals to 1 by x and g of x is equals to suppose 1 by x minus 2. Okay, so then what will be the domain of f? What will be the domain of f?
All real
All
numbers
reals except 0.
Except 0.
And domain of g will be all real except 2.
2.
Because at these 0 and 2, we are getting infinity. That's why. Now, what will be domain of f composite g? So I will find out in two ways. First, I will find out the expression and then domain. And secondly, we use these two steps. So expression means, let's find out what will be the expression of f composite g of x. Okay. So f composite g of x is nothing but f of g of x. So that means we have to apply f on g of x. But if you apply g on x, it will be 1 upon x minus 2. And if you apply f on this, it will be 1 upon x minus 2. It means x minus 2 will come into numerator. So that is x minus 2. So if you find out the expression of f composite g is nothing but x minus 2. And we know that it is nothing but an equation of line. So from expression, we are getting that domain is whole real number, correct? But if we go through our steps, then what will happen? So by our steps, so by the steps. Okay, so first thing is find out domain of f, domain of g. This we already completed. Second step says remove all those x belongs to domain of g for which x g of x is not a part of domain of f. But what is domain of f? Domain of f is real number minus 2. So that means there is only one point which is not a part of domain of f, and that is equal to 2. So let's see when g of x can become 2. Okay, so we have to solve this expression g of x is equals to 2 to find out all those x for which g of x is equals to 2. That means 1 upon x minus 2 should be equal to 2. So this says that 2x minus 4 is equals to 1, right? Just cross multiplication. So this means x is equals to something 5 by 2, correct? 4 will goes here, so 4 plus 1, 5, and then 2. So 5 by 2. So which means g of 5 by 2, if you compute, this is equal to 2. And 2 is not a part of domain of f. So that means we have to remove x is equals to 5 by 2 from the domain of g. So this will implies we have to remove x is equals to 5 by 2 from domain of g. And then whatever set is left, that means whatever domain of g is left, that is your domain of f composite g. So this will implies domain of f composite g, domain of f composite g of x is actually domain of g minus with this removed point. So domain of g minus with x is equals to 5 by 2. So that means the whole real number minus of 2 points, 0, because we are removing 0 from domain of g, and 5 by 2. So now this is the actual domain of f composite g. So if you just go by the expression, then you may not get, then you don't come across that, okay, at these 2 points, the f composite g is actually does not make sense, because f composite g does not say that, okay, we have to apply, we have to apply two functions one by one. So first of all, for input value, g of x should be well defined, and then for g of x, f of g of x should be well defined. So that's why we have to go by these two steps to correctly find out the domain of f composite g. Okay, so I'll revise it again. Here I have missed one thing, so I can write it here.
If I may ask one question.
Yeah.
So in the graph of FOG, F composite G, what will be the position at 5 by 2, madam? It will undefined?
Yeah, it will be undefined. Because see, if you compute graph, you need some expression, right? So this is not a valid expression which, at x is equals to 5 by 2, it's actually not defined, correct? But if you just go by the expression and find out the graph, then it will be defined. So because expression, it's very simple, right? X minus 2. But if you treat x minus 2 as composition of these two functions, f and g, then at x is equals to 0 and at x is equals to 5 by 2, f composite g is not defined.
Madam, in Desmos, we can do composition also, isn't it, ma'am?
I don't think in Desmos we can do. I haven't tried yet. So
Okay. We will try, madam, later.
Yeah, we can try.
Okay. Thank you.
So in Desmos, can we define function? F of x is equals to 1 by x. Yes, we can define. So let's try now. 1 by x.
Screen is not shared.
Yeah, I'll share. First of all, let me check.
Okay.
Is well defined or not. F of g of x. Yeah, they are no. In decimal, We can say, but we have to zoom. So much zoom is there.
Yeah, maybe you'll have an asymptote, isn't it, ma'am? It will not meet at 5 by 2 or
In
0.
Desmos, we actually cannot say it's not.
Okay.
So these two functions I have defined. The red one is f of x is equals to 1 by x. Green one is f of x is equals to x minus 2. And this is blue and it says a composition function. So it is actually giving us the image at 0. But 0 is not in not the point of domain. Okay. So the Desmos is not working here. Because first it is finding out the expression and then drawing the graph. But if you go logically, because we first we are applying g and then we are applying f, so that's why we have to remove those points for which uh, g of x is not defined, and then remove those points for which f of g of x is not defined. Okay. So
Good,
then
ma'am.
Is Desmos giving graph for f of x?
yeah,
It is
this is
giving.
Can we see that once again?
yeah. So, so
So
it
at,
is
at 0, what is
So at 0, it kind of increasing the values very rapidly. So for example, 0.069 or 0.0668, we have 14 point something values.
It will never meet the y-axis.
It kind of reaching towards infinity.
No, but even at infinity, it will not reach, madam.
It won't reach.
So
Yeah,
it
there
is
will be very
asymptote.
little gap between y-axis and the graph.
Yeah. So it is why it's an asymptote, no, madam. Like it will
Hmm.
not. It will never touch the y-axis.
Correct. It will never touch the y-axis.
Yeah.
But for composite function, for this function, it is actually giving the value at 0.
0, comma minus 2. Yeah.
okay.
But
Okay, ma'am. Thank you.
So it is not the Desmos is not taking that rule 1 and rule 2 into consideration.
it's just computing the expression and then giving us.
Finally, finding out the equation of the line.
Right.
Okay, madam. So we will not rely on Desmos for
Response for
finding
finding
the
domain.
domain of composite function.
Correct.
Okay, good, madam. Thank you.
Okay. Is there any doubt related to composition of function still?
Please explain it one more time.
Yeah, sure. So what you have to do, if you want to find out domain of f composite g of x, what do we want? First of all, we want g to be defined at that particular x, and then we want f to be defined at g of x. So here, first, what we'll do, we obviously will find out domain of f and domain of g. Then if you want to find out domain of f composite g, you have to take care of all those x for which f of g of x is not defined. So that means we have to remove all those x from where we have to remove. We have to remove all those x from domain of g, because ultimately we can take only those x which belong to domain of g. Okay, so we have to remove all those x from domain of g for which g of x is not a part of domain of f. Okay, and once you remove all those x, whatever left, that is your domain. So so that means domain of f composite g of x is actually domain of g minus these removable points, whatever points we get in steps 2. So if you remove all those points from domain of g, you will get domain of f composite g. Now instead of f composite g, if we have g composite f, then what will do? So what will be domain of g composite f of x? So here again, so what is g composite f? G composite f means g of f of f. So first we are taking x as an input. We are applying f on that. So that means f of x should make sense. And after f of x, we are applying g on f of x. So that means g of f of x should make sense. So here also, first step remain as it is. That means finding domain of f, domain of g. But here in the second step, we have to remove points from domain of f, because first we are applying f here. So remove points from domain of f for which this f of x is not a part of domain of G. And whatever left in domain of f, those will be our domain of G composite f. So then domain of G composite f is actually domain of f minus the points in step 2. Okay, because again the logic is the same, that we want first f of x should be well defined, and the second thing we want G of f of x should be well defined. That's why we have to remove all those points for which f of x is not part of domain of G. Okay, that's how we can find out domain of f composite G and domain of G composite f. Okay, so I'll ask you one question. So suppose A is domain of f1, B is domain of f2. So I think this type of question is in your assignment, but let's see. Then what will be the domain of f1 plus f2? So I'll give you 3 minutes to think, and then you can answer in the chat box. Okay. So if A is a set of domain of f1, if A is domain of f1, B is domain of f2, then what will be the domain of f1 plus f2? Answer in terms of A and B. Okay, in terms of set A and set B. And again, f1 plus f2 is defined like this. f1 plus f2 of x is equal to f1 of x plus f2 of x. Okay, so the answer is correct, A intersection B. Because what do you understand by domain? Domain means at those points the function value should be well defined. So what we want to find all those x for which f1 plus f2 of x should make sense, right? So if f1 plus f2 should make sense, this is same as f1 of x plus f2 of x should make sense. So that means for x f1 and f2 should be well defined. So from this I can say that x belongs to domain of f1 and x should belongs to domain of f2. And we know that whenever this and comes in, it actually represents the intersection of two sets. So this one implies x belongs to A and x belongs to B. So which will implies x should belongs to A intersection B. So which will implies domain of f1 plus f2 is nothing but A intersection B. And it is true for every other expression. So that means f1 minus f2 also, f1 into f2 also. So for f1 by f2, we have to remove all those points where f2 becomes 0. Then we can say that the domain of f1 by f2, if you apply the quotient or division, then in that operation, we have to remove all those points where f2 becoming 0. Because we know that anything upon 0 does not make sense. It does not make sense, right? Okay. Is this question clear? Any doubt?
Yeah, clear, madam. This idea we'll be using in when we are finding the domains like addition of functions and subtraction of functions,
Mhm.
division of functions. So that is why we are learning this, isn't it, ma'am?
Yeah,
The
correct.
concept which you have
Ma'am,
told
this
now.
idea will be used in every composite functions or what?
Yeah, some sort of composite function. So here it is a composition of two, three functions, you can say. We are applying separately. So this type of, yeah, you can use this in any type of operation. So if F1, F2 is there or any other type of operation is there, you can use the same ones. So whenever you find out domain, you just have to take care of the things that, okay, for this input, our expression should make sense. That's all. So if you understand this particular thing, then you can easily find out for any domain of any type of function. So now let's go to exponential functions. So exponential functions are very special type of function. So exponential function. So exponential function is defined like f of x is equals to some a to the power x. So here what we are doing, we are taking power of some real number where this a can be your any real number. So depending on this particular a, the exponential function behave in different ways. So for example, if you take a between 0 to 1 or if you take a to be any other values, it depend on the function that it actually the exponential function will change accordingly. So for example, I'll take two values, and for negative values we can judge similarly. Just a second. So suppose here, if you, first of all, I'll just say if you take a is equals to 1, then this f of x will be 1 to the power x, which is equal to 1. Which is equal to 1. So that means for a is equals to 1, it will just a constant function. So let's look for values other than 1. So here we'll take two cases. So the first case is when the value of a is positive. Again, we don't take the negative values of a, because obviously the square root and all things will create a problem. So for example, if I want this to be a function from real number to real number, the square root of that function, the cube root, fourth root should be well defined. So that's why we stick with a belongs to real number and a is strictly greater than 0. These two conditions. So whenever exponential function is defined with some value of a, that a should be a real number, but a positive real number, strictly positive real number. So here we have two cases. So first case is when a is between 0 to 1, and another one is when a is strictly greater than 1. Because we know at 1 it's just a constant function. And why we are removing the negative values, but we know that for negative values the square root, the fourth root will create some problem. It will give us a complex numbers, or it won't define. So that's why stick with the positive numbers. So when a is between 0 to 1, the graph of exponential function behaves in a decreasing way. So that means something like this, and the x-axis is the asymptote for this particular graph, and it will intersect at some point. So we'll find out the intersection point 2. And here, when a is strictly greater than 1, the graph of exponential function behaves like an increasing way. Okay, and it's a kind of obvious, because we know that if a is between 0 to 1, if you increase the power of a, the value will decreases. And
I have a
similarly,
doubt, ma'am.
yes,
Irrespective of the value of x, if a power x graph is same as a power minus x?
a power x's graph is same as a power minus
If,
x.
is
No, no,
this
no. It will change, it will got reflected over y-axis. So for example, if you have the graph of, suppose I have 2 to the power x's graph. So the graph of 2 to the power x will something like look like this. But if
okay?
you compute 2 to the power minus x, so for negative values, we get a positive values. For positive values, we get a negative value. So it will get reflected over y-axis. So something like this. So these are the changes. Okay, fine.
Okay, thank you.
Ma'am,
Thank you.
in the 2 to the power x concept, the x should be always positive, no?
No, no,
The
no. X could
should
be
be always
anything.
positive.
X could be anything, right? Because we know that 2 to the power minus 100 also I can define. This is same as 1 by 2 to the power 100. So it's a real number. So X could be any real number.
And ma'am, what about minus 2 to the power x?
minus 2 to the power x also, yeah, then we have a problem. That's why I'm saying that whenever
It
you
will go to
take
minus infinity, no? The y will be minus infinity, I guess.
2 to the power minus x or
No,
minus
no,
2.
minus 2 to the power x.
Yeah,
Minus
then
2
it
to
is
the
not a
power.
function because for some values it is not well defined. If you take x is equals to 1 by 2, then under the root of minus 2 is not a real number, right?
Yeah.
You get it? So that's why we restrict ourselves for this a strictly greater than 0 case. We don't want the value of a to be negative because of the complex numbers. We can get a complex number there. Okay. So this is a one case when the value of a is between 0 to 1, and another case is when the value of a is strictly greater than 1. So in this case, the graph will be some sort of decreasing kind of behavior we have, and here we have increasing behavior. So here we will check some of the properties. So first thing is what will be the y-intercept. So here we want the value of y to be equal to 0. Then which value of x we should check? And this is a graph of a to the power x. This is also a graph of a to the power x. What will be the value of x here? Sorry. I'm taking the value of x to be 0. Then what will be the value of y? So it is e to the power 0, which is same as 1. So here the y-intercept is 1. Similarly, here also the y-intercept is e to the power 0, which is equal to 1. So in both cases, the y-intercept will be 0, 1. Okay. 0, 1, 0, 1. Is that clear? Okay.
Yes,
So
ma'am.
now let's check some of the limits, or we can say the end behavior of this particular function. So here in this case, if I find out limit x going to infinity, a to the power x, then what will be the value? What will be the answer for the first one?
Infinity.
It tends to infinity.
Infinity.
Yeah, that's the case. Here, the value of a to the power x never
Touches.
it never touches the x-axis. So that means it is coming close to x-axis. That means it's going to 0, not to minus
Yeah.
it, right?
Yeah. 0.
0. And as x goes to minus infinity, it's going towards infinity, right?
Infinity.
These are two limits. Similarly here, limit x going to infinity, limit x going to minus infinity, a to the power x. So what will be the first limit here?
Infinity.
Infinity, correct. Here,
Here it tends to 0.
0. So in both cases, x-axis will work as an asymptote for these functions, a to the power x. Is that clear? Okay. So now I'll ask another question. So is a to the power x is a 1 function or not? So e to the power x is 1. So what do you guys think?
It's 1 function only, ma'am.
Correct.
Horizontal test, it is passing.
Correct. By horizontal test, we can say that it is a 1 function. Now, if I say that a to the power x is a function from real number to real number, is this an onto function?
E power x. Yes.
No, it is asymptote, madam. One particular
Correct. It cannot cross this
touch the x
x-axis. So that means if I draw a vertical line here, y is equals to -1, it never touches or intersect with our graph.
any points.
For y is equals to -1, we don't have pre-image. So the answer is no. So here we get that e to the power x is a 1 function always, but if you define it this function from real number to real number, it cannot be an onto function. Correct? But here, if you restrict your domain, so that means in place of real number, if you restrict your domain to r plus, so that means all positive real number, then can you say that it is a onto function?
Now, R plus, will it contain 0 also?
No, it won't contain 0.
Okay, so R minus, R plus, both will not contain 0, madam.
Strictly positive numbers.
Then it is onto.
Correct. It will be onto because for every y, we can get an x for which the function will map to that particular y. So that's the one thing we do. So here, So this simply implies that f of x is equals to e to the power x. If you define from real number to real number, then yes, it is 1, 1, 1, 1, but not onto. But if I restrict the domain f of x, the domain of f of x from real number to r plus, again r plus means strictly.
Why it's not onto the first one?
Because by a vertical test or by the graph, you can say
Okay.
right? We cannot get pre-images for negative values. Right. So, but if here, if you restrict the domain to r plus, then we can say that yes, it is 1, 1 as well as on. Right. So that means it is 1, 1 as well as on 2. If you restrict domain to r plus. So that means if we restrict domain to r plus, sorry, I am saying domain. If you restrict codomain to r plus, so in that case, we can say that e to the power x is bijective function. Okay, and then for every bijective function, we can define an inverse. And the inverse of this function is actually a logarithmic function, which we will cover in week 6. So that's why we proceed to logarithmic function. So we define logarithmic function as inverse of exponential functions. Okay. So is these two things are clear? So in first case, since the codomain is a real number, that's why it's not an onto function. In the second case, we restrict codomain to strictly positive real numbers. So because of that thing, we can say that yes, it is 1, 1 as well as onto. And we know that if a function is 1, 1 and onto, it will be a bijective function. So in this case, a to the power x.
Restricted the codomain, then how it becomes the bijective? I mean, onto.
Yeah, it is already 1, 1, but for onto what we want pre-image. So from the graph, we can simply say, since it's approaching to 0, right? So if you take any value of y, so if you draw any vertical line, sorry, any horizontal line,
It touches
will
it.
intersect.
Okay, I got it. Yeah.
So it will become onto. So that's why it will become bijective, and we can define an inverse. And that inverse is known to be a logarithmic function, which we cover in the next week. Okay, so this is all about the exponential function. Now, what happened in so many, what you can say, so many, some physical expression are there. So some expression defining oscillations, right? Speed of a atom or whatever. Some physics expressions are there. So in those expressions, this. Okay, so in those expression, this word E is actually mostly used. So this E is a number which we can define as a limit of a sequence, but I don't think you guys are familiar with limit of a sequence. So it's a limit of this particular sequence, limit tending to infinity, 1 plus 1 by n to the power n. So if you are comfortable with sequence and if you find the limit of this sequence, it comes out to be a real number, and that number is denoted by E. So E is just a symbol to denote this particular real number. Because what happened, this real number does not have any finite decimal expression or any, what you can say, finite values. So if you write the expression, it will always go on. I mean, you cannot write it over a finite paper or with a finite sequence. So that's why we use some symbol to denote such a number. So these type of numbers are known to be rational numbers also. So E is there, pi is there, right? So these numbers do not have any finite expression type of thing. So for example, I can write 2.1419 something up to, suppose I'll write 1,000 numbers here and I'll end somewhere. But for these numbers, you cannot write it using a finite numbers. So that's why we use symbol for those numbers. So we define E as a limit of this particular sequence. So if you are not familiar with sequence, that's okay. It's just an information you can take. So this E is mostly covered in some experiments. So if you do some experiments, or you have already learned that in so many physical experiments, we got this type of E. So that's why it has a significant in maths also and in physics also. So we kind of separately understand what is the function f of x is equals to e to the power x. Okay, and this is known to be natural exponential function. Okay, so natural exponential function. So the value of e will lies between 2 and 3. So if you compute some of the terms of E, or if you just find out the values of E, so we can prove that the value of E is actually lies between 2 and 3. So we can say that E is nothing but strictly greater than 1. Okay, so if E is strictly greater than 1, we know that f of x is equals to e to the power x, how it works, how it behaves, right? So this will imply that this will be the graph of e to the power x, and it will intersect y-axis at 1. Okay, so from the graph, we can say that it is an increasing function. Is this a 1 function, e to the power x?
Yes, ma'am.
Correct. It will be a 1 function. It won't be an onto function because we cannot find out pre-images for negative values, and all the same steps work for as we have learned for e to the power x. Okay, so this is the e to the power x function. Similar to, we are just taking some particular value of a and treating that as a separate function, e to the power x, a natural exponential function. Okay. Is there any doubt from exponential function?
Ma'am, will we not find a range for composite function and exponential function?
For composite function, again, the range is a tough part because we have to consider all those. But by the graph or by the observation, you can find. But for exponential function, the range is kind of obvious. So can you guys tell me what will be the range of e to the power x? What will be the range of e to the power x?
Positive real numbers?
Correct, positive real numbers. Because for any positive real numbers, we can find out the pre-image. Again, just by drawing a vertical line. This line intersect here. So for this x naught, for this y naught, I'll get this x naught as a input. Okay, so that means for exponential function, the range is nothing but positive real number. That's why we restrict the codomain to positive real number, the range set, to gain onto functions. Okay. So yes, so I think I have covered almost all topics from week 5. Any doubt you guys have? Anything which is not clear?
Can you please explain once again that example which you gave for finding the domain of the composite function? That example.
Okay, yeah. So this this one, right? So here what is our issue? So issue is, if you go with the expression, you may not get the exact domain, or you count some other points too in your domain. So this is a wrong way to find out the domain of composite function. Go by the expression. So what we have to do, we have to follow these steps. So first of all, find out the
So,
domain. Yeah.
no, ma'am. No, ma'am.
Okay, so that means find out the domain of G, find out the domain of F, then remove all those points from domain of G, and then whatever points are left in domain of G, that will be our domain of F composite G. So here we have two functions. First is f of x is equals to 1 by x, and g of x is equals to 1 by x minus 2. So domain of f will be real number minus 0, domain of g will be real number minus 2. So now first step is over. Second step says remove all those points from x belongs to domain of G. And why I'm taking domain of G? Because I want to find out domain of F composite G. So in F composite G, we have to first apply G. So that means whatever x you are taking, on that x, your G should be well defined. So that means G of x should be well defined at first place. So that's why we have to remove all those points from x belongs to domain of G, for which if you apply G on that point, because we can apply, because we are removing from domain of G, so we can apply G on that particular point. So if you apply G on that particular point, whatever output you'll get, that output should be a part of domain of F. And if it is not a part of domain of F, we have to remove that point x. Because again, if it is not a part of domain of F, the f of g of x does not make sense. And by composition means we are applying function one by one. First we are applying g, we are getting some output. On that output we are applying f, and then again getting some output. But for applying f of x or f of g of x should make sense. Okay, so this is our first step. So here what we did, we want to find out all those x for which g of x is not part of domain of f. But what is domain of f? Domain of f is nothing but real number minus 2. So the only element which is not a part of domain of f is this particular 2. Right? That means this 2 is the only element there which is not a part of domain of f. So what we'll do, okay, first we will find out that x for which g of x is equals to 2, and then remove that x. But because for removing I need to know what will be the value.
For G, X should not be in the domain of G, no? Then why are we checking G of X equal to 2?
Yeah, because we
Should
don't
not be
know
2.
which x
No,
we are
X
looking
should
at.
not be 2. Not G of X should not be 2.
G of x should not be 2. That's correct.
Why?
We want that x for which g of x should not be equal to 2, right? But how do you find out that particular x?
No, G of X function is 1 by X minus 2, right? For G of X, X should not be 2. It is not
correct.
that G of X should not be 2.
Oh, I have missed here. So this 2 should not be here. There should be 0 here. So I have written wrong as domain of f. So I thought f is 1 by x minus 2. Actually, g is 1 by x minus 2. Thank you. So here we have to find out all that particular x for which g of x is equals to 0. So we have to remove that x for which g of x is equals to 0. Now it's correct. Yes, you have a valid point. Because again, the steps are okay, the steps are clear, but here I assume I write it wrong. I mean, domain of f, I consider it wrong. Okay.
Yeah.
So here we have to consider that x for which g of x is equals to 0. Okay, I mean, remove that x for which g of x is equals to 0. That means 1 upon x minus 2 is equals to 0. So that means there is no point, right? Because this cannot happen. 1 upon x minus 2 is equals to 0. This cannot happen for any x. We cannot find out. Because ultimately, if you solve this, you will simply get, if you cross multiply it, you will get 1 is equals to 0, which is not true. So which will imply there is no x. There is no x in domain of G for which g of x is not a part of domain of f. So in this case, we don't have to remove anything. So here domain of G.
So we have to remove 2 from the domain of F, no?
Yeah. So that's why I'm saying domain of G is same as domain of G composite F. Thank you. I missed the point here. So that means here domain of F composite G will be same as domain of G, and which is nothing but real number minus 2. Correct. So I mean mistakenly written there real number minus 2 and then do the calculations.
It will be true for G of F.
Oh, yeah, correct. If we compute G, then also we have to do, I mean the point will be something else. So let's compute the domain of another composite function. So what will be the domain of G composite f of x in this particular case? So again, domain of G is real number minus 2 and domain of f is real number minus 0, right? Because G is 1 by x minus 2 and f is 1 by x. Okay. So then what will be the domain of G composite f of x? So here what we have to do, we have to remove x belongs to domain of f for which f of x is not a part of domain of G, but domain of G is real number minus 2. So what we'll do, we'll find out those x and then we will remove it. So find x such that f of x is equals to 2. So that means 1 by x is equals to 2. Right. So that means 2x is equals to 1. So that means x is equals to 1 by 2. And now we will remove this 1 by 2 from domain of f. So this will implies remove 1 by 2 from domain of f. So which will say is domain of G composite f will be domain of f minus this 1 by 2 also. So now from domain of f, that means from real number we have to minus 2 points. So one is 0 and another one is 1 by 2. 0 and 1 by 2. Now this is correct, right? Is this clear now? Fine.
Can you explain it once again, the second one?
Yeah, sure. So we did the same steps. We find out domain of G, domain of F. But here I want to find out domain of G composite F. So first of all, f of x should be well defined, right? So that means I have to consider all those points which belongs to domain of f only. Because if I take any other point, then f of x is not well defined. So first we have to restrict ourselves to domain of f only, right? But from that domain of f also, I have to remove all those points for which g of f of x is not defined. That means g should be applicable over f of x. That means f of x should be a part of domain of g. So what do? We find out all those x for which f of x is not a part of domain of g and then remove them. But for removing, but there is only one point which is not in domain of g, and that is 2. So we will find out all those x for which f of x is equals to 2 and then remove that. So we will find that x for which f of x is equals to 2. But what is f of x? F of x is 1 by x. So that means x should be equal to 1 by 2. If I want 1 by x to be equal to 2, x should be equal to 1 by 2. So now for this x, the g of f of x is not defined, because for this particular x, if you compute f of x, it will become 2, and if you try to apply g on 2, then it is not well defined, correct? Because g is 1 by x minus 2. That's what we do. We'll remove 1 by 2 from domain of f. So what is domain of f? Domain of f is already real number minus 0. So here we have to remove 2 points. We have to remove 0 since f of 0 is not defined, and we have to remove 2 because g of 2 is not defined, and f of x is equals to 2 when x is equals to 1 by 2. Sorry, we have to remove 1 by 2 because at 1 by 2 f of x is becoming 2 and g of 2 is not well defined. So that's why we have to remove 2 points in this case, and those 2 points are 0 and 1 by 2.
Yeah, I understood now. Thank you.
Okay, thank you for that mistake. I also forgot. Okay, anything else? This is not clear. We still have some time. I'll share this PDF over the calendar. Yes, Nari.
For quiz 1, are we going to have any revision sessions?
Yes. We have scheduled 2 revision sessions for quiz 1. So one session in one session will cover week 1, week 2, and another one will cover week 3 and week 4. Okay.
When any idea when it is, ma'am?
Yeah, I'll just let me see. It is somewhere near to quiz only. I mean, because before quiz we have to complete week 5 too, right? Week 5 and maybe week 6 lectures too. So revision session 1 is on 19th Feb and revision session 2 is on 21st Feb. 19th and 21st.
Okay, thank you.
Okay.
What about the timing?
Timing will be usual 8 to 10.
8 to 10, okay.
Because week 6 deadline is very close. I mean, 26th.
But generally, week 6 the deadline will be
pushed forward,
shifted, postponed.
But this time it is not the case. I mean, it's not the case. They have strictly mentioned us that they won't push the deadline. So
Every time it is mentioned, madam.
but I don't know. This time they told us that you have to plan your session accordingly. They won't accept our request.
Okay.
I don't know they will push or not. So we'll try to say, because 3 days is, I mean, you guys already busy with quiz, and after that you have to complete week 5 and then week 6. So
okay.
Okay, so that's all from my side. If you guys have anything to discuss, we can discuss. Otherwise, see you in the
What will be syllabus for quiz 2?
quiz 2. So for quiz
Yes.
2, you can say 70 or 75% syllabus will be from week 6 to 8, 5 to 8. And there will be some questions from 1 to 4 too. So syllabus is whole, but the weightage is different.
You have not covered that inverse function.
Yeah. So inverse function, So inverse function means a function which is 1 and onto both. So this is bijective function, right? So
No,
bijective.
like what Madam is telling is like Professor told, no, it will be identity function. X you will get.
Composition.
Yeah,
So
composition.
for bijective function, we can define another function. So suppose we have a function. So suppose f is a function from a to b, and it is a bijective function. Then we can find out another function g, which will be a function from b to a, in such a way that if you find out the composition, that f composite g of x or g composite f of x, these two composite function will be equal to the identity function. And this function g is known to be the inverse of f. Inverse of f, and denoted by f inverse. Okay, so this is the whole thing. So if you have a bijective function, then for that function, it is possible to find out another function g from the range or codomain to a, codomain to domain, in such a way that if you find out these two composite function, f composite g or g composite f, both will be equal to identity. So, and this function g is kind of unique. So that means there will exist only one such type of function which have this property, f composite g and g composite f. And because of the uniqueness, it is known to be a inverse of a function f and denoted by f inverse. Okay. So this is known to be inverse of a function. So finding inverse is simple when you have linear type of functions. That means equation or linear with quotient. Then it's easy. You just have to express y in terms of x and then replace it. So that's how we can find out. But in general, it's not that easy. So for example, okay. So for example, if I have this function, f of x is equals to 4x plus 7 upon x minus 9. Okay. So you can check that it is a 1, 1 and onto function. How I can say? Because I can explicitly find out the inverse of this function. How you will find out the inverse? So suppose I'll write y is equals to 4x plus 7 upon x minus 9. So what you can do, you have to express x in terms of y now. That means y of x minus 9, 4x plus 7. So this is same as xy minus 9y is equals to 4x plus 7. And this is same as 4x minus xy is equals to 7 minus 9y. And this is x is equals to 4. Again, the codomain domain, you guys can take care, right? So here the domain will be real numbers minus 9.
4 minus y.
Right. And codomain will be what the whole real number, I think you can take.
Okay.
So here 4 minus y is equals to 7 minus 9y. That means x is equals to 7 minus 9y upon 4 minus y. So here this function will work as the inverse of given function f. If you find out the composition, so suppose I'll define g of x to be equal to same expression 7 minus 9x upon 4 minus x. And now if you find f composite g and g composite f, you will get x only. So this is one way to find out the inverse, and it's a very easy way. Just express x in terms of y and then follow the things. I mean, consider that to be your g of x. That will work as an inverse. Okay. So, but this is a main concept that if you have a bijective function, then it will possess an inverse, and that inverse will have this particular property, and it works both ways. So both ways means if you find the inverse, you can imply it will be 1, 1 and onto. And if it is 1, 1 and onto, there will exist an inverse. So it's vice versa. Converse is also true. Okay. Clear, or I just mentioned it too fast?
I understand.
Okay.
Thank you.
Yeah, madam.
Yes.
Thank you for the session. I think we are closing now. Huh?
Yeah.
Okay. Good night, madam. Thank you for the session.
Thank you guys for joining.
Thank
Bye.
you.
Thank you.
Good night.
Shall we have, I have doubt on activity questions. Shall we discuss it on tomorrow?
Yeah, we can discuss tomorrow.
Okay. Thank you.
In the open session or solve with us, whatever.
Okay. Thank you.
Ma'am, you will upload this PDF on calendar.
Yeah, I'll upload the link of PDF over the calendar. You can go and download it from there. Okay.